Hello everyone, I am Kausal Patel from Mechanical Engineering Department at Mahatma Gandhi Institute of Technical Education and Research Center, Navsari. In this video, in Introduction to the Vibration, we are going to study the basic elements of vibratory system, then mathematical modeling of any physical system, then simplification of that model by finding out equivalent spring stiffness and equivalent damping coefficients, and finally the classification of vibrations. Basic elements of vibratory system. So any physical system can be broken into these basic elements of vibratory systems. Those are spring, mass or inertia, and damper. So generally spring is used for storing potential energy, as we know that whenever a spring is deflected by applying some external force, some work is done on the elastic constraint, and that's why that work is stored in the spring due to the deflection. That energy is known as strain energy. Okay, it is one kind of potential energy, or we can say internal energy. Okay, so by means for storing potential energy, spring element is used. Next element, that is mass. Okay, so it means for storing kinetic energy. So whenever mass possesses some velocity, it is having kinetic energy, and kinetic energy that is necessary to keep body in motion. So here for vibration, this energy is more important. So for that purpose we are going to use the mass element. Okay, then during vibration there is always some energy loss in the form of heat or by any other means. Okay, so depending on different damping provided to the system, there is a vibration loss, or we can say energy loss during the vibratory motion, and further amplitude of vibration keeps on reducing, and finally the system comes to rest. Okay, so for that energy dissipation during vibration, that is generally represented by an element called damper, so which is nothing but the damping resistance provided to the system. Okay, so if the system is provided some damping, then we can use damper element. Okay, now in any vibratory system there is an exchange of energy from one form to another form, as we have discussed earlier. So whenever the system is deflected from its mean position, so due to the deflection the energy is stored in the form of strain energy due to the deflection, because some work is done against that elastic constraint. On relieving of that force, the system starts vibrating, it starts accelerating toward the mean position. So generally the energy enters the system by the application of external force, and that energy is stored in the form of potential energy, or in this case for spring, mass and damper system, it is stored in the form of strain energy. Now on releasing of that body, that energy is converted into kinetic energy. That kinetic energy is again going to convert it into strain energy as spring is deflected. Okay, so this conversion of energy keeps on repeating and system continues to vibrate. If there is no damping is provided, then this vibration continues infinitely. Okay, now if some damping is provided, then the amplitude of vibration gradually decreases as the energy dissipated in each cycle of vibration, and finally system comes to rest at mean equilibrium position. So if damping is provided, then we can use damper element having damping coefficient C. Okay, so using these three basic elements, spring, mass or inertia and damper, we can build a mathematical model of any physical system. So our next topic is mathematical modeling of system by lumping of parameters. So most of machines are made of different components which are made of certain materials having various properties. Okay, so that material must have some elasticity, it is having mass, right? So that are the main properties related to vibration. Now during motion there is also some energy loss would be there due to friction or due to some kind of damping resistance, right? So any physical system can be broken into number of basic elements and we can build a mathematical model. So most of machines or structure made of elastic members, okay, so they will have infinite degree of freedom. It means the system would be continuous system, or we can say distributed system. So to analyze such system we need to convert this continuous system into a system having finite number of degree of freedom. Okay, we can do this by lumping of parameters. Okay, so as the name suggests, a lumped parameter system concentrates on individual property of system. For example, let us take a mass. Okay, system would have number of masses, so we can consider the whole mass is concentrated at the center of gravity of the system, and then we can do analyze. On the similar lines, the property of elasticity can be considered by the lumping of its elastic response by showing it as a simple spring element having a stiffness K, so that this spring is going to represent the elastic property of that system. Okay, here stiffness of spring would further depending on the type of material, its property, okay, and its dimensional parameter also. So if a model is carefully developed by identifying each and every element of vibratory system, then we can get reasonably accurate solution. But the mathematical model developed initially that would consist of number of elements like number of springs, number of dampers, it is having number of masses. Okay, so that initially developed model, it would have more number of degree of freedom, and that's why they are difficult to analyze. We can simplify the model by finding out equivalent mass, equivalent stiffness and equivalent damping coefficients, so that we can reduce the number of elements and make the system simple. Okay, now by analyzing this simple model we can get approximate behavior of the system. Okay, to understand that, consider a forging hammer as shown in figure. It consists of a frame, anvil, hammer, elastic pad and foundation block. So as shown in figure, frame and anvil is separated from the foundation block by using some vibration isolator, that is elastic pad. Okay, foundation block that is further placed on soil. So here we need to identify each and every important parameter which is affected to the behavior of system. So here we can see that there are three number of masses, but here mass of frame and anvil can be combined. Okay, now as frame and anvil is separated from foundation block by means of elastic pad, we have to consider mass of foundation block separately. Okay, then elastic pad and soil, it is having both elastic property and damping characteristics. So for that purpose we need to consider two spring elements and two dampers. Okay, so here we can build a mathematical model like this. Okay, there is a combined mass frame and anvil. It is separated from the foundation block by means of elastic pad. So in between them, here damper element and spring element for elastic pad. Okay, here this spring element would represent elastic characteristic of the elastic pad, and this damper element is going to represent damping characteristic of elastic pad. Same way for soil, we have also considered the stiffness of soil and damping of soil. So for that purpose, the spring and damper element is used. Now here there are two masses, frame and anvil and foundation block. So this system is having 2 degrees of freedom. Okay, so we can do analysis of this system, but it would quite difficult as compared to a system having single degree of freedom. Now by finding out equivalent stiffness, equivalent damping coefficients, we can combine these two masses. Okay, so for this mathematical model, it is further simplified as this model. Okay, so here we can see that we have to find out equivalent stiffness and equivalent damping coefficient, so that we can simplify the model like this. Okay, so here this model is having only single degree of freedom and it is very easy to solve. Okay, so by simplifying the model, we can get reasonably accurate solution. Now our next topic, that is simplification of mathematical model and how to find out equivalent spring stiffness and equivalent damping coefficients. Okay, so simplification of mathematical model. So we have already discussed earlier. To simplify the mathematical model, we need to find out equivalent spring stiffness, equivalent damping coefficients, equivalent mass. Okay, equivalent mass could be easily find out by simply summing up all the masses present in the system, and by considering whole mass is concentrated at the center of gravity of system. Okay, now we need to find out equivalent spring stiffness and equivalent damping coefficients. Okay, so that is further depending on whether the springs and dampers in the system are series or in parallel. So first of all, we are going to find out equivalent spring stiffness of a system in which two springs are in series. So here for this system, we can see that two springs having different stiffness K1 and K2, they are in series. So this system can be simplified by finding out equivalent spring stiffness Ke. Okay, now here for this system, we can see that both springs are subjected to same force, and that is due to weight. Okay, so the induced spring force in spring 1 and spring 2, that would be similar to this force mg. Okay, so we can see that here for this particular case, fs1 and fs2, that is spring force for spring number 1 and spring number 2, that would be equal to mg. Okay, so let spring number 1 and spring number 2, they are taking mass m1 and m2 respectively. Then we can say that in this case mg is equal to m1g is equal to m2g. Okay, now we can see that the total deflection of system, let it be delta, then it would be the individual deflection of both spring delta 1 and delta 2. So total deflection of actual system would be sum of the deflections of individual springs. So we can write down delta is equal to delta 1 plus delta 2. Okay, now this model is simplified and this is our equivalent system. So here total deflection that would be same, and it would be delta, and it is equal to delta 1 plus delta 2. So as we have discussed, deflection of equivalent spring that would be equal to the deflection of actual system. So here we can write down delta is equal to delta 1 plus delta 2. Okay, now we already know that here in this particular system the mass is not in motion. It means it is in static equilibrium under the all forces acting on that system. So here spring force Fs would be equal to mg as we have discussed earlier. So for spring number 1 we can write down Fs1 is equal to m1g, and for spring number 2 we can write down Fs2 is equal to m2g. Now we also know the equation of spring force that is directly proportional to the deflection. Okay, so Fs is equal to k into delta. K, that is constant of proportionality, and it is nothing but just stiffness. Okay, so by making this delta as a subject we can get the relationship delta is equal to Fs divided by k. So for equivalent spring it would be equal to mg divided by ke, and for spring number 1 it is m1g divided by k1, and for spring number 2 m2g divided by k2. So in this equation we can put the values so that we can get the relation like this: mg divided by ke is equal to m1g divided by k1 plus m2g divided by k2. Okay, now as we already know that mg is equal to m1g is equal to m2g, so that's why we can get the final relationship, that is 1 upon ke is equal to 1 upon k1 plus 1 upon k2. So here in this case where springs are in series, we can say that the reciprocal of equivalent spring stiffness is equal to the sum of reciprocal of individual spring stiffness. Okay, by using this relationship we can get the equivalent spring stiffness. Now our next case, that is two springs are in parallel. Okay, so in this case this is our actual system. Here we can see that two springs are in parallel having different stiffness k1 and k2. Mass is suspended on this spring. So we know that total force mg, it is distributed over these two springs k1 and k2. So let k1 takes the load, that is let it be m1g, and load taken by spring number 2, let it be m2g. So these two forces distributed over these springs. So here in this particular case, when springs are in parallel, we can write the relationship like this: mg is equal to m1g plus m2g. Okay, here both springs are having different stiffness k1 and k2, so that's why mass is not equally distributed. So in this particular case we can see that the deflection of both spring would be equal, and it would be equal to the deflection of actual system. So here delta is equal to delta 1 is equal to delta 2. Okay, so this is our actual system in which two springs are in parallel. Okay, this system could also be represented like this. Here these springs are also considered as in parallel. Here we can see that if this system is having deflection delta in that direction, then also the springs having same deflection, this spring would going to be extend through delta, and this spring would going to compress as delta. So deflection of spring would be similar. Okay, now we can get equivalent system by finding out equivalent stiffness. So here, to find out equivalent stiffness, we know that the deflection of equivalent spring would be equal to the deflection of spring 1 and deflection of spring 2. So delta is equal to delta 1 is equal to delta 2. Now we have get the relation mg is equal to m1g plus m2g. Okay, so for the system in equilibrium, here we can see that the system is not in motion, so spring force would be equal to mg. So for the system in static equilibrium, weight is equal to spring force, so mg is equal to ke into delta for this equivalent spring system. Okay, for spring number 1, m1g is equal to fs1, and for spring number 2, m2g is equal to fs2. Now we already know that spring force is equal to k into delta. Okay, for equivalent spring, it is equal to fse is equal to ke into delta. For spring number 1, it is equal to fs1 is equal to k1 into delta 1, and for spring number 2, fs2 is equal to k2 into delta 2. So from this relation, we can write down this relationship: ke into delta is equal to k1 into delta 1 plus k2 into delta 2. Okay, as delta is equal to delta 1 is equal to delta 2, finally we can get the relationship equivalent spring stiffness ke is equal to k1 plus k2. So for this case, when springs are in parallel, the equivalent stiffness can be found out by summing up individual spring stiffness, and that's how we can simplify the model. Okay, so this is about equivalent stiffness. Now equivalent damping coefficients. So for that purpose, our first case, two dampers are in series. So here this is our actual system in which two dampers having damping coefficients C1 and C2, they are in series. So for that we can also get equivalent damping coefficient by applying the theory of springs in series. So we can get the similar relationship: 1 upon Ce is equal to 1 upon C1 plus 1 upon C2, and using this relationship we can find out equivalent damping coefficient. The same theory as in case of springs in series is applied, because in spring system we know that Fs, spring force, is equal to K into delta. It means it is directly proportional to the displacement of spring. Okay, so it is having linear behavior. Same way, the damping force Fd is equal to C into x dot. So here we can also see that the linear behavior, damping force or damping resistance, it is directly proportional to the velocity. So we can apply the same theory and we can get the similar relation. Now two dampers in parallel, we can also get the similar relation: Ce is equal to C1 plus C2. Okay, so that's how we can simplify the mathematical model by finding out equivalent stiffness, equivalent damping coefficients, right? And that's how we can reduce the number of elements. Now our next topic, that is classification of vibration. So here in this block diagram, the whole classification of vibration is given. So according to the actuating force, vibrations are classified as free vibration and forced vibration. Then according to the external resistance, it is classified into undamped vibration and damped vibration. Okay, next, according to the motion of system with respect to axis, it is further classified as longitudinal vibration, transverse vibration and torsional vibration. Okay, then according to the behavior of vibrating system, it is classified into linear vibration and non-linear vibration. Okay, furthermore, according to the magnitude of actuating force at a given time, it is classified as deterministic vibration and random vibration. So we are going to see each classification one by one. Okay, first one, that is based on actuating force, and the vibrations are classified into free vibration and forced vibration. So this part we have discussed earlier. In definitions, we have studied what is free vibration, what is forced vibration, what are the difference, right? So if an external force is applied to disturb the system to get a displacement from the mean position, okay, then we are going to simply release the body. It starts vibrating, and after the vibrating starts, due to its elastic nature, okay, there is no external forces applied during vibration, so that type of vibration is known as free vibration. Okay, and the frequency of free vibration, that is known as natural frequency of the system, and it is the most important parameter for vibration analysis, right? So there are many examples of free vibrations, like simple pendulum, simple spring mass system, lateral beam, or we can say cantilever beam, then a torsion system. Okay, so these are the various examples of the systems which are having free vibrations. So the system, once deflected from its mean position, then on the removal of that force, the system starts vibrating, that is free vibration. While in case of forced vibration, the vibration, it is due to the applied dynamic external excitation force, which could have periodic characteristics or random characteristics. Okay, so whenever any system is subjected to such external excitation force whose magnitude or direction or both are going to change with respect to time, then the system is going to vibrate depending on the frequency of external excitation force. Okay, for example, vibrations in IC engines, electric motor, centrifugal pump, due to some rotating unbalance or reciprocating unbalance. Okay, so these are the examples of forced vibration. Next classification, that is based on whether external resistance is provided or not. So we already know what is damping. Damping is nothing but external resistance provided to the vibratory system, and if external resistance is provided to the vibratory system, then there is energy dissipation during each cycle, and that's how we can reduce the amplitude of vibration. Okay, so according to the external resistance provided or not, vibrations can be classified as undamped vibration and damped vibration. So if there is no external resistance is provided to the system during the vibration, then such vibration is known as undamped vibration. So in undamped vibration, the system would vibrate with natural frequency of the system. Okay, in undamped vibration, theoretically, vibration continue infinitely and the amplitude of vibration would remain same. It would remain constant. It is not going to decay with time. But in real practice, there is always some damping present in the system. For example, due to the air resistance, or we can say due to the viscosity of air, then due to the internal friction at microscopic level, okay, that is the friction between molecules. Okay, due to such negligible damping, the amplitude of vibration gradually reduced and finally system comes to a rest. Okay, but if such negligible damping is there, then still it is considered as undamped vibration, because this energy losses, that is very negligible. Next type of vibration, that is damped vibration. Okay, generally damping is provided to reduce the amplitude of vibration, to reduce the undesirable effect of vibration, to control the amplitude of vibration. Okay, so that's why the external resistance is provided by using damper or other such devices. So by providing damper, we can apply the damping to the system so that during each cycle some vibration energy is going to dissipate it, and that's how we can reduce the amplitude of vibration. So here the displacement versus time plot for both undamped vibration and damped vibration are plotted. Here we can see that in undamped vibration the amplitude of vibration, it remains constant and the vibration continuous. Okay, it is not going to stop. But in case of damped vibration, we can see that the amplitude of vibration gradually reduces with time. So here the system would comes to rest at theoretically infinite time. So that is the main difference between undamped vibration and damped vibration. Okay, next classification, that is according to the motion of system with respect to the axis. Now to understand this classification, we need to consider a weightless shaft of which one end is fixed and at the second end the disc having mass m is attached. Now here, as shown in this figure, if the system vibrates along the neutral axis of shaft, then we can say that the vibration is longitudinal vibration. Now if the system vibrates in the perpendicular direction, then the vibration is known as transverse vibration, or we can say lateral vibration. Now if the system is having limited angular oscillatory motion above the neutral axis of shaft, then that vibration is known as torsional vibration. Okay, so same things we have discussed here. Now our next classification, that is according to the behavior of vibrating system. Okay, so vibrations are classified into linear vibration and non-linear vibration depending on the behavior of vibrating system. So system is made of basic elements that are spring, mass and damper. These three elements are more important for any vibratory system. If the behavior of these three basic elements, spring, mass and damper, is linear, then we can consider the vibration as linear vibration. Okay, so in simple spring, mass and damper system, the force related to spring, that is Fs is equal to K into delta. It means the spring force is directly proportional to the displacement of system. So it means its behavior is linear. It is linearly proportional to the deflection. Same way, force due to the mass, that is accelerating force, or we have considered inertia forces in D'Alembert's principle. So this force is having magnitude m into a, mass into acceleration. So the force is directly proportional to the acceleration, so its behavior is linear. Same way for damper element, we have considered that damping force Fd is equal to c into x dot. It means damping force is directly proportional to the velocity. So if the vibration is linear, then the differential equation governing this motion, it would also be linear, and linear differential equations are much easier to solve as compared to non-linear differential equations. Now in case of non-linear vibration, any of these three basic components behave non-linearly. Okay, so in many cases, for some type of spring, it does not behave linearly. Okay, its behavior would be non-linear. Then if spring is loaded beyond its elastic limit, then there is a plastic deformation and the and the behavior would no longer remain linear. Okay, so in such cases the vibration would be non-linear. Okay, beside this there are certain types of damping which is having non-linear behavior, such as solid damping or structural damping, then slip or interfacial damping. So this type of damping is having non-linear behavior, and if system is subjected to such vibration, the equation governing the motion that would no longer remain linear. So these non-linear differential equations are quite difficult to solve. Okay, our next classification, that is according to the magnitude of actuating force at a particular given instant of time. So if the magnitude of external excitation force at any instant of time is known and it is predictable, then we can say that this kind of vibration is deterministic vibration. Okay, so for example, vibration caused by rotating unbalanced masses in machine, that is one of the common example of deterministic vibration, in which we know the particular frequency of external excitation force. Okay, so it is deterministic vibration. While in case of random vibration, okay, magnitude of external excitation force we cannot predict at any instant of time. Okay, its magnitude would change in unpredicted manner. So such vibrations are known as non-deterministic or random vibration. For example, vibration caused by earthquake. Then in musical instruments there is an acoustic vibrations. It is having random characteristics. They are subjected to forces which are having random characteristics. So such vibrations are known as non-deterministic vibration or random vibration.